Hello everyone. In this video, we will be looking at what Kubernetes is and how it is used in the software world, how it is used to deploy an infrastructure for your application to different cloud providers. So it's a software that takes care of your application deployment and scaling it onto a bunch of computers, which is called a Kubernetes cluster. Those clusters can be made out of physical computers or virtual machines. The basic building block of Kubernetes is a pod. A pod is essentially an application that you put inside a container, and that container is then wrapped around a few more things, and then collectively we called it a pod. A pod adds a few things on top of container, which is labels and annotations. Labels are very useful. They are used by the other services in Kubernetes cluster to pick up what pods they want to work on. So if a label has got a label version equals 1, that pod will be picked up by that service. Restart policies, termination control, they are very self-explanatory. Security policies and more, you can configure security policies and whatnot in the pod configuration. So how a pod is created? This is the process. We write the code, we package that in the container image, for example, Docker container image. We wrap the container image in a pod, which means that we write the YAML representation of the pod, and we mention that this is the image that we want to put inside the pod, and then you run it on Kubernetes cluster. This is a typical YAML for a pod. We mention the API version. Everything in Kubernetes is done through an API, and the API server of Kubernetes exposes a REST API that is used to create pods, do things on cluster, get all the pods that are running on the cluster, and that API is basically the entry point of everything you can do on Kubernetes. The next thing is the kind. This is the kind of the object we are creating. Obviously, it's a pod. Metadata gives it a useful information. The name of the pod will be hello pod. These are the labels that we just mentioned. This pod will have two labels. One is zone and other one is version. And then, so this is the definition of the pod. These are the things that are basically wrapped around the container. And then under the spec, you have the definition of the container itself. So the name of the container will be this, hello CTR. Image where the container will be created from is provided here. You can have your registry configured with Kubernetes, and then you can provide your if you provide your account name and then the name of the image and its tag, it will pull that image from there. And then the what ports you want to expose on the container. And this is the visual illustration. Inside the pod, you have got this container, and pod adds these things on top. So the process of deployment of a container to a pod to the cluster is you define a YAML, you post that YAML to the API server. The API server authenticates and authorizes your request because it's an API endpoint. It will look at who is sending the request and if you are allowed to do that operation. Then the YAML is validated. It checks if the YAML you've created is fine, and then the scheduler deploys. Scheduler is another component that that looks at what pods are ready to be deployed, and it schedules them to be deployed on a node which is healthy. That means that has got enough resources available to entertain that pod. So a node can have one or more pods. So the scheduler basically looks at the cluster and picks up a node that can handle the workload of that pod. And then the kubelet something called kubelet monitors it. Kubelet is something that is present on the node. We will explain that in a bit. Pod can have multiple containers. This is the IP address of the pod, and these containers can communicate with each other using the IP and the port that they are listening on. This is how pods look when they are deployed on a cluster. We can see that we've got 5 computers, and they all are on different networks. So this one is network A, and node 5 is on network A, node 2 and 3 are on network B, and node 4 is on network C. It's not necessary that this will be the case, but if this is the case, and you deploy your pods onto one or many nodes from these cluster, what will happen is the pods will have their own network. So say, for example, if this pod over here is deployed to node 5, and that one is deployed to node 4, and this one is deployed to node, say, for example, node 1, right? The pods will still be able to discover and communicate with each other because they have their own local network. So they are not dependent on the network of the node that they are running on. So what's inside a node? A node has got 3 things basically. A kubelet. A kubelet is a piece of software by Kubernetes that handles the node being part of the cluster. So it registers the node with the cluster and says that this node is actually part of that cluster. The container runtime, which is the process that is able to run containers like Docker container. Container D is, I think it's provided by Docker, is a runtime that can run, that can help run containers on that machine. Network proxy is a piece of software that handles the networking part of the overall implementation. This is a worker node basically, and we can deploy pods onto this node. And now we have seen what a worker node looks like. Now we have looked at what the worker node is. What we want to look at now is this image here. This is the Kubernetes official documentation. The Kubernetes cluster is divided into 2 parts. One part is called control plane, and the other part is called data plane. The control plane is a bunch of computers from within the cluster that is used to run the services needed for the Kubernetes to function. So if you have, say, a cluster of 10 computers, we can say that 3 computers from those 10 computers are control plane. That means they run the services needed by Kubernetes, and the remaining 7 will run our applications. That is the data plane. In the control plane, we have API server. API server is the API that we hit to do anything on the Kubernetes cluster. We have etcd, which is the data store where all the configuration that we post to Kubernetes is stored. All the information about what the cluster is, what pods are there, what deployment controllers we have, everything that is related to configuration of our cluster is stored in that data store. Scheduler is a component that schedules new pods onto healthy nodes. So this is all basically the brains of the Kubernetes cluster. The other part, which is the data plane, is just computers that will run our pods. Every node has got a kproxy and kubelet that we just explained. And then the third part in here will be the pods that we deploy to these nodes that run our application. Okay, pods are immutable. It means that they cannot be updated. They shouldn't be updated. The purpose of the pod is to just run the application, and if there is something wrong with the application or the pod, it will simply be destroyed and a new one will be created. They can also be short-lived, means that if a pod is doing something that is temporary, for example, it needs to run a bad job and the pod will be created, the container will be created, the application will run, and when it has done its job, the pod will be destroyed. kubectl is a command line tool. Anything you want to do on Kubernetes cluster will be done through kubectl command. For example, if you want to get all the pods, you just run kubectl get pods, and it will give you all the pods running in the cluster. Kubernetes namespaces are a way to partition your cluster logically. So the biggest use case is if you want to create 3 different environments, your development, your testing, and production, you can use namespaces. You can create a namespace with name dev, a namespace with name test, and a namespace with name production. Namespaces are also useful if you have multiple applications that you want to deploy on a cluster. So you can maybe create a namespace for each application. It really depends on what scheme you develop to use namespaces, but they are basically a tool that you can use to logically divide your cluster. Deployment is a way to deploy your pods to the cluster. There are many controllers in Kubernetes control plane, and one of the controllers is called deployment controller. It handles a deployment object that we create, and it looks at that object, looks at that configuration, and it makes sure that the state of the deployment of the pods mentioned in the deployment object is kept all the time as it is expected. Or in the Kubernetes way, there are 2 states. There is observed state and there is desired state. Desired state is the state that we mentioned in the config, and the observed state is the actual state of the cluster. And the deployment controller basically its job is to make sure that the observed or the actual state is always identical to what we have mentioned in the configuration, which is the desired state. This is a deployment YAML. The deployment YAML has got obviously deployment. We give it a name. Replicas 10 means that it will deploy 10 pods, 10 identical pods, and it will make sure that they are up and running all the time. Selector is hello world. So it will pick up the pods that has got a label name app, and its value is hello world. Minimum ready seconds is the amount of time that it will wait after creating a pod and see that it's up and running for that period of time before it goes on create a new one. Strategy is the deployment strategy. Now we have mentioned rolling update, and it basically depends on these 2 things. The max unavailable whose value is 1, it means that when we are rolling out an update, if we have an application running in 10 pods and now we have an updated version of that application that we want to deploy, it will destroy 1 pod out of those 10 and create a new pod with new application and replace that with the new one. And then it will go on to the next one, and it will repeat that process for 10 times to replace all the pods. Now, if we have mentioned max unavailable 2, it will destroy 2 pods and create 2 new ones and replace those 2 with the new ones. So this is the configuration that you can choose according to what your needs are and how it best fits your needs. So you can choose this configuration according to your needs. And then we have template. Template is basically the template of the pod. For the pod, we have just given it a name, hello world. So this label is used here to pick up that pod, and then the spec has got the container details. This is the image name. This port should be open, and then hello pod is the name of the container. There is something in between deployment and pods. It's called replica set. It's replica set that is actually responsible for scaling and healing, right? And this part over here from replicas all the way to min ready seconds is a separate type of object. It's called replica set. So replica set is basically is a thing that performs the actions required for scaling and self-healing. Now we have seen at deployment, we have seen at pods, we have seen how deployments are used to deploy pods. But how about if we want to access an application that is running in a pod? That's where service comes in. Services are used to access our applications deployed to the pod, and they have stable IP address, stable port, and stable DNS. And the reason for that is we have said that pods are temporary, they just come and go, and we can't use their IP address to access the applications. That's where service comes in. It load balances the pods or that are running your application. So basically what you do is you hit the service rather than the pods, and the service sends the request to a healthy pod and gets you the response back. Here on the right we have the YAML representing a service. We are creating a service object that will be handled by a service controller. Metadata is the usual stuff. In the spec we have the type of the service. We have mentioned node port here. There are two other service types that are used widely that we will explain that in a bit. And then we have mentioned the port. This is the port where the request will be sent to the pod, and the node port is the port that will be opened by the service to the outer world. So here we can see that the service is load balancing between these 4 pods, and the client hits the service. Here's the selector part of the configuration. How does a service know which pods to load balance? It depends on the labels. So these 3 pods have got the labels zone and version, and they will be matched, and this service will pick these pods to send requests. There are 3 different types of services that are widely used. Cluster IP is the type of service that is used within the cluster, so you can't access that service from outside the cluster. If an application that is running in a pod needs to access another application that's running in another pod, it can hit the cluster IP service that is load balancing the other application pods, and they can interact in that way. Node port, we just saw the configuration for. It's for outside world. We can hit that service, and it will send the request to the pods and get us response back. Load balancer type is mainly for cloud. So when you deploy this kind of service onto a cloud provider, it will provision that cloud provider's load balancer, for example Nginx in AWS case, and that load balancer will be able to load balance your requests. Ingress is a type of service which can load balance different services. So we have said that a service load balances different pods. Ingress can load balance different services. So here we can see that we have created an ingress, and there are 2 services here, and so it can read out the traffic based on the routing rules that we define as part of the ingress configuration. So here we say that this domain will be sent to that service, and this domain here will be sent to Hydra service. And then it has got also the path configuration that if a request like this comes in, we are sending it to Shield service, and if we have /Hydra in the URL, then we are sending it to Hydra service. So Ingress is very useful when you want to have a common load balancer that can send requests to your different applications. Now the next thing is storage. How storage works, and how can different pods access to different storages. There are 3 basic elements. There is storage class, there is persistent volume, there is persistent volume claim. Now, every storage provider implements a plugin, it's called CSI plugin, which is to basically standardize the access of storage from within the cluster. So we create a storage class which basically defines what the storage is, who is the provider, what kind of storage it is, right? So this is sort of the metadata of the storage, and we create persistent volume claim that is used by a pod to actually claim the storage. So think of this as a class. If you're familiar with object-oriented programming, this is the class, and that is the definition of an object of the class, and the pod will use that definition to claim its storage, and the volume will be mounted onto pod in the container of the pod. Kind of the object is storage class. Here we mentioned the API version. Provisioner is the provider of the storage. Here we are using EBS-CSI, and these other configurations can be looked up in the documentation, and you can use the ones that that you need. Persistent volume claim is the actual object. So we mentioned the name of it that we'll be using in the pod, and then access mode, read write once. There are two more access modes. Again, look in the documentation and see which one you need. And then we say that we need 50 gig of storage, right? And then the storage class name is fast local, which is this one here. So this storage will be created based on that storage class, and then this persistent volume claim will be mentioned here in the pod definition. So the storage volume will be mounted onto container. The next thing is config maps and secrets. The config maps are just key value pairs which are provided in form of a YAML configuration, and when these are posted to Kubernetes, they will be made available to pods as environment variables. There are two ways you can create config map in form of key value pairs, and if you have more values, we can also use this syntax. So config map is used to provide environment related data to pods. So you have different URLs or different database connection strings for dev environment, stage, and production. So you can use config maps for each type of cluster to provide these values as environment variables to the applications. How about passwords and API keys and the data which is sensitive? We create a secret kind of object to provide those values. In the secret configuration, we basically base 64 encode the data and provide that encoded string here. It's not really secure, but it is like one way of hiding the data. And here we can see we have encoded username and password in base 64, and we have created this secret. And if a pod is using data from this secret, it will be, the username and password will be available as environment variables, and it will be decoded for the pod to use. And this is how you inject the values from the config maps into the pod definition. So we can see the spec in this in the container spec. We have an env section in which we say that we want to create an environment variable of name first name, and the value from mentions that where the value will come from, and then we mention the name of the config map and the key inside that config map. And then similarly here we are mapping the family attribute of config map onto the last name, and in the pod in the container these values will be available as environment variables. Stateful sets are similar to deployment. they deploy pods and they manage the number of pods. They are different in one way that they create the pod names in a very predictable way. So they will use the service name. There's a scheme that they use to generate the names of the pod in a very predictable manner. So if they, for example, if we have replicas, 3 replicas, they will create pod names as, for example, ABC service dot pod 1, ABC service dot pod 2, ABC service dot pod 3. And if any of the pods goes bad, it will create the new pod with the same name. So what's the use of it? Its use is to say we want to have a pod that runs our database, and we want to connect to our database. We can use that pod's name to connect to that database, and the volume it creates is similar. It gives predictable names to the volumes, and so those pods, the same pods, can have the same volumes attached even if the pod goes bad and is terminated and is created again. The naming scheme basically makes sure that the same pods with the same name attaches to the same volumes. Okay, that's enough of theory. Let's see everything in action. Right, so I have 2 applications for a car dealership. The car dealership is called JAC, hypothetical name. JAC backend is a project which is a microservice that exposes these endpoints, and JAC frontend is a React application that interacts with that backend to get data and save data. The backend database we are using is MongoDB, and we will deploy that MongoDB instance onto a separate pod. Now let's go through the Kubernetes configuration. Here I have a bunch of YAML files. I will go through them step by step. Let's go into the DB directory, and I have a file with name storage.yaml. What we are looking at here is the secret configuration. We mentioned that you can provide secret in form of this configuration, YAML configuration. I'm using string data attribute here to provide the username and password for the database in plain text. But we have mentioned before that we can encode it in base64 and provide that encoded string here, and we can simply use data like that. But for simplicity, I'm just using string data. So this will create a secret object in our cluster. The next thing we are creating is a storage class. The storage class is a type of storage that defines a storage that it will be available for the cluster whenever it's needed. The important bits are provisioner. When we say no provisioner, it means it is going to provision local storage. By local storage, it means that it will provision the storage on the node. Volume binding mode wait for the first consumer means that do not create any storage until it is requested by a pod. Right. The next thing we create is persistent volume. Persistent volume is basically the actual storage that is created on the node, or if it's by a storage provider like Amazon Block Storage. This object basically determines that how much storage will be created, and this storage is made available for us depending on what's the volume binding mode defined in the storage class. So this definition here is essentially where the storage will be mounted, what's the reclaim policy, it's retain. Reclaim policy means that when a container using a storage is terminated, what to do with that volume. So retain means it will not be deleted even if the container using that storage is deleted. The other important bits are storage class name. We have said that this is the storage class name, and this basically tells what kind of storage you are going to provision. So no provisioner means that it will be a local storage on the node that it is deployed to. Right. And this here node affinity is basically telling that what node to use to create this storage. So we are creating this storage on the node whose role is who has got a label with the name role, and its value is Jackos MongoDB node. Right. The next object is persistent volume claim. Now this object is used by a pod configuration, and it has to match this configuration over here. So a pod will say that this is my persistent volume claim. It's like a request to a persistent volume to get a storage for a pod. We give it a name, Jackos PVC storage class name. Again, this is the class name we have defined above. Access mode is read write once. This access mode is also used as a label to match the persistent volume claim with the persistent volume here. And then the storage, it needs to match what we have defined in the persistent volume. So this will be mentioned in the pod configuration, and this will match with the persistent volume, and it will be created when the pod requests for the storage for the first time, because we have mentioned wait for the first consumer in the storage class. The next thing is StatefulSet. StatefulSet is equivalent to deployment, but the only difference is that it will give predictable names to pods. In the spec, we will mention a service name, and I will explain what this service is and what it does in a bit. Replicas is 1. We just want one pod running the database. Selector is what pod to select. So this pod we will define at the bottom of the this configuration file. And here is the template of the container that we want to deploy. So we provide the metadata, we give the pod that role, which will be selected by the service, and then in the spec we have got a node selector. Node selector means that this node should be selected for the pod, and then we have got the container definition. We give its name, image is Mongo, and then these are the environment variables being injected into the container. We have got the database names. Its value is hard coded for now for simplicity. We've got the username. Its value is coming from the secret ref. The secret name that we have created is Jackos Mongo secrets, which is up here. So we are referencing that secret as a name here, and the key we want from that secret is username, that is defined here. So that username will be injected into this environment variable. Similarly, we inject password, and then we mount volumes. The first volume we are mounting is it's called secret volume, and the mount path is etc mount db secret, and it's read only. You can't update that once it's created. And then the second one is MongoDB data, and mount path is data/db, and this mount path is basically the mount path that we have defined in the persistent volume. And then we specify the volumes that will match these volume mounts. The name is secret volumes, and then the secret name we provide is this one here, and then the name is MongoDB data, and persistent volume claim is jackass PVC that we have defined up here in the persistent volume claims. Now notice that what is common between these two sections, the volume mounts and volumes. If you look at this name here, it is matching with that name. So what we are saying is mount these secrets onto this directory, and if you look at this one here, it matches that name, and we are saying that mount the PVC, that storage, onto this directory here. And then the next one is a service. Why we need a service? We need a service to get the IP address of the pod. We know that this pod is long lived because it has got a predictable name. So we create a headless service. By headless service, what we mean is it is a cluster IP service, but we say cluster IP none. That means that it will create a service and it will create the endpoints. By endpoint means it will have a collection of the IP addresses of the pods that it is load balancing, but it will not have an IP address for the outer world to hit it. Why do we do that? We do that to access the IP address of the pod that is running the database, so that we can use that in our application to access the database. And this service is deployed onto and this service basically selects this pod that it will be load balancing. This is all the database configuration stuff. It will create one pod and it will host our database MongoDB, and we will connect to our database from the other pods that will be running our backend services. Now let's look at the backend services for a minute. This configuration file has a bunch of objects that will help us deploy our backend service that will connect to that database. The first thing we see here is ConfigMap. We give it a name, and there is only one configuration item in this ConfigMap, and that is the headless Mongo service that we have created as part of our storage YAML file, as part of our database setup, this one here. So the service name can be used as host name for the database. Coming back to the backend deployment configuration, so this is our config map. It will this DB host will be mapped into the pod that we will see in a second. The next thing we create is the deployment object. Now why this is deployment object? Because these pods do not have to have predictable names. They can come and go if because this application is stateless. If something goes wrong in the backend application or the pod that it is residing in, it can just be destroyed and replaced with a new pod. We give it a name. We have said that replicas is only one. For simplicity, we are just running one replica. You can give it 2, 3, or however many you want to run. Selector selects the pod that it will deploy, and then revision history limit, it can go back 5 steps. Minimum ready second is wait 10 seconds for the newly created pod and then create the next one. Strategy is rolling update that we have discussed in previous sections, and then we have got this template here. Now this is the pod template. We are creating a pod with the label called app, and its value will be jackbe app. We can see that this is highlighted here in the selector section of the deployment, which means that the deployment will select these pods. The next section is affinity section. affinity section basically helps us to define some rules. For example, this rule here is node selector terms. We say that if a node has got node group of jack be in node group, then this pod can only be deployed to that node. This is the container definition. We have got a name, the image which will be pulled and container will be created from. The env section injects the environment variables that will be read from either the secret that we have created in the secret object in the storage config. Let's go back and see these ones here, or this one here that is created in the jack cause be config, which is the config map up here, right? Username, password, and db hostname will be available for the container as environment variables with these names: Mongo username, Mongo password, and db host. The next thing we are creating is the service, so that we can hit the pods from the outside world. We are calling the name, we're calling it jackbe svc, type is cluster IP, so that we can hit it from outside. We will hit the service at port 80 and the target port is 3001, which is the port that our container will be listening at. And then the selector section selects the name of the pod that it will load balance, which is up here in the template. We similarly look at the front-end application deployment config. Similarly, we have a config map. There are a bunch of endpoints. These are basically, so this is the domain that we'll be using for Ingress. I'll show the Ingress configuration in a minute, and these are our URLs for the backend service that we can hit. Again, the deployment service, we similarly define the affinity rules to say that these pods will only be deployed to the nodes that has got node group as jack fe node group. And then the container definition is here. It is using the same image, but it's a different tag, so that's going to be a different application. And this is another way of injecting ConfigMap. You simply say env from, and then you say ConfigMap ref, and give the name of the config map that you've created. So what it will do is it will take all of that and inject these as is with the same names into the container as the environment variables. And then similarly we create a cluster the service that will load balance these pods, and the port for this application is 3000. The port for this service is same as the backend service, which is 80. Let's look at Ingress configuration. We talked about Ingress, that it can load balance between multiple services. We give it a name, and then we specify the rules here in here. Ingress class name is nginx, as it will load the nginx load balancer when we deploy it to the AWS. Now this is the rules. So if the host is jackcause.com, if the request is coming from this domain, then what it will do is it will forward the traffic to jack fe svc, which is a front-end service that we have defined over here, this one here, that is load balancing the front-end pods. And then we have got a another host rule, which is jackcause.be.com, and any request coming from this domain will be forwarded to the service for the backend, which we have defined over here in the backend, and that is obviously load balancing the backend pods. Ingress controller is not enabled or installed by default in the Kubernetes cluster. So what you have to do is, if you want to use Ingress, you have to install it, and this is the command that you can use to install Ingress. So we will be using that command in a bit to install Ingress controller. And then the last but not least, our cluster config. So AWS provides you a tool. It's called EKS-CTL. EKS basically lets you define your cluster configuration similar to what a Kubernetes cluster object looks like. So this kind here, cluster config, is not a Kubernetes object. It is a custom object that is provided by AWS, and we can basically define everything about our cluster. We have the name of the cluster, we need the region, which is EU West 2, basically London, node groups, and now we have defined, we can get rid of that node group here, we don't need that. There are 3 node groups. There is Jack FE node group, there is Jack backend node group, and there is Jack backend DB node group. And in each node groups, we have got the instance type T2 micro for each of them. Desired capacity is 3 for backend and front end. So there will be 3 nodes for the backend, 3 nodes for the front end, and 1 node for the database. And then the volume size is 10 gig. SSH, if you want to enable it, you can do. If you don't want to enable it, you can simply ignore that or remove that. I have provided my public key here, which means that I can SSH into the nodes if I need to. It's generally not needed, but it's really up to you and how you want to design your infrastructure of the application. Right. I think we are at a point now where we can run the commands and we can set up the infrastructure for our application. Let's get into it. I will go to command line. I'm already in the Kubernetes directory, which is this one here. Obviously, the first thing I want to do is I want to create my cluster. So I will use the tool that is provided by AWS. I will say EKS-CTL create cluster -f cluster.yaml. What this command will do, it will take everything that is written here and it will understand the configuration, and it will create all the nodes infrastructure for us, and it will give us a Kubernetes cluster. This is going to take a while and I will skip through the process. Alright, it took about 15 minutes and it has created our cluster. So going back, we ran that command with cluster YAML configuration, and it created a cluster for us. And now if we head over to AWS, we will search here for EKS Elastic Kubernetes Service. That's what we are using to create our cluster. We can see that we have our cluster created, it's active. If you go inside the cluster, you can see all the resources and all the nodes created in it. Now if you go to compute, you can see that these are all your nodes. So for example, if I open up the first one, I can see things in it. The one thing that I want to show you is this thing here. So the node group for this node is Jack BE node group. That means that the pod that will contain the backend application will be deployed to this node or any other node that has got the same node group. Other than that, there's a lot of information we can see here. There are currently 2 pods running, and these are pods that are required by Kubernetes to function. So at the moment, we have 6 nodes. They some of them will also behave as the control plane, and the others will contain the pods that are running our application. Right, so we go back to cluster, and now going back to the command line again. The next thing I want to do is I want to first of all create the storage. So I want to set up the database first of all. So let's go ahead and create the database pod. Now from here on, I will be using kubectl, that is the Kubernetes command line tool, to create everything. because now we are doing everything inside the Kubernetes cluster. Apply -f, and then the name of the file that we are going to run is storage.yaml. Let's run it. Now here we can see that it has created the secret, it has created the storage class pvc, stateless Mongo deployment, which is a StatefulSet, and then the Mongo service. Now what we can do here is we can actually look at these things. kubectl get, let's see the pods first. So we can see that this pod here, JCOS stateful Mongo deployment 0, this is the name of the pod, and if this pod is destroyed and it creates a new one, it will have the same name. So that's why having the predictable pod names is beneficial in case if you're running the DBs on it. We can see the state, it's container creating state, which means it hasn't been fully created yet, it's in the process. It will create that in a sec, so we'll check the status in a bit. Now let's see the services. kubectl get svc, get svc. Here we can see there's a Kubernetes service that is part of the control plane that is used by Kubernetes to function, and this is our service that we have created, JCOS headless Mongo service. And we can see that its cluster IP is done because we don't want an external traffic to hit the service. This will be used from within the cluster for the pods that are running backend application to connect to the database. I think we can get secret. There you go. So it says that the cluster has created the secret. It has got 2 entries in it, and this will be used by the pods, backend pods. Let's get the pods again. We can see it is still in container creating. You can see that our database pod is running. The next step we are going to do is we are going to create our backend pods. So we'll simply go kubectl apply -f deploy backend YAML. We can see that the ConfigMap is created, the deployment is created, and the service is created. Now if I go again and say get pods, we can see that there's a backend pod created as well, and its state is container creating. If I go kubectl get services, we can see that there's a backend service also created, and it's a cluster IP service. Now it has got an API, so this cluster IP can be used to hit the service from outside. And then kubectl get pods. Now we can see that both our pods are running. The database pod is running and the backend application pod is running. Now the next thing I will do is run the front end file and create the pod for the front end. kubectl apply -f deploy front end, and again we can see that now we're going to see the third pod, which is the front end pod, and kubectl get svc, and this is our service that is created for the front end. kubectl get pods again, it is still creating, so we'll just wait for some time and check the status again. Now it's running, and we can see that all 3 pods, front end, back end, and database, are running. Now we have mentioned that we will use Ingress that will provision a load balancer provided by cloud provider, which is AWS, and it will provision an Nginx, and we will hit the Nginx, and Nginx, based on the domain name, will send request to either the front-end service or back-end service, these ones here. So let's see how it's going to happen. So we will go install Ingress. So this is the command that will enable or install the Ingress controller. So what we will do is we'll simply paste that command here and run it. It will create everything that it needs to run the Ingress controller. So we can see that it has created a bunch of stuff that is needed for Nginx to run. So we can see here it has created the Ingress class. So what it will do is it will provision Nginx load balancer in AWS, and then we can apply our kubectl apply -f our Ingress configuration, so that our rules are put in force. Kubectl get Ingress, we can see that our Ingress is created, and here we can see that it will be handling requests from these two domains, jackcos.be and jackcos.com. Now if we head over to AWS, let me go back again. I had opened the load balancers. We have one load balancer created for us, and I need to find the IP for this load balancer so that we can hit it. Right, copy that. I will go to network interfaces. I will search for that ID, and then from one of these we are going to get the public IP. Now how we are going to make use of these domain names, I'm going to go to my host file, and I will redirect the traffic from these two domains to that IP address, like so. Now if I go to my browser and if I go jackcos.com, maybe there's an application error here. If I go to any other URL, there you go, you have your application running. Now we know that the front end is working. Let's try to save some data into the database. Anything, and add vehicle. Apparently it's saying there is some error, but I think this is an application level error. We can debug by looking at the application. Okay, so apparently there is something wrong with the front-end application that we need to debug, but what I wanted to show here was that we have got our application being served from the front-end pod, and when we can actually look at if it's able to save data in the database. 5, let's see, that's the registration number, buying date is 3, description is anything, price is anything, any number, add vehicle, and we can see here the request that is sent to jackcos.be.com/vehicles, which is a post request, and the payload is whatever data we entered in the form. We got the the status code as 201, which means that it has created the record in the database at the backend. So there you have it. This is how you create your application infrastructure with just a few commands, and you have your application up and running in the cloud with no time. And similarly, if you have your updates, for example, when I fix this bug, I will just run one command. I will push my image to the Docker Hub repository or wherever you are hosting your images, and then I will just run one command to roll out the updates, and it will take the new image and replace all the pods. And that's pretty much your application infrastructure automated. And obviously you can look at your configurations and improve them as per your needs. For example, if you want to create a dynamic storage, you wouldn't use no provision. For example, you want to use the Amazon Elastic Block Storage by AWS. So you will mention that provisioner here, and there's a whole lot of stuff that you can mention here. You will have to look at the documentation on what options you can use. But yeah, this was just a quick introduction of what Kubernetes is, how it can be used to deploy applications to the cloud. So now you have your pods deployed to relevant node group nodes. If we go here and say, if we look at this node, and we can see that this has got a front end pod deployed to it, which is running. And if you look at the node group for this one, it's jack fe node group, and so it is deployed to right node. If I look at this one, for example, and if I look at the node group, this is the DB node. So the DB pod should be deployed here, which is this one here. So now if you want to delete your cluster, because running a cluster obviously it will cost you money, and once you have seen that, if you are in process of development, once you have seen that your cluster is working fine, and now you want to delete it, you will use the same command that you used to create the cluster, which is EKS ctl delete cluster -f. The same configuration file that you used to create the cluster, you will use the same config to delete it, and it will delete everything in order, so that there are no resources that are running on the AWS cloud. So it will delete, when it delete nodes, basically it's going to delete everything, the pods and obviously whatever is on those nodes. Right, so the cluster is deleted. As you can see, we issued a command right here to delete the cluster, and it just went through the same process to delete the node groups and everything, the control plane and the other node groups from the cluster, and all the resources that were provisioned from the AWS, they are now released and deleted. Now if you go back to AWS console, and if you go to Elastic Kubernetes Service, you can see there are no clusters here. Similarly, if you go to load balancers, you can see there is no load balancer. So everything is deleted as part of that command. So there you have it. We created an application infrastructure from the YAML configuration, and the time it took was not more than 30 minutes. This is very useful when you want to roll out updates for your application, when you want to manage your application infrastructure as configuration. And let me know about your thoughts in the comments below, and I'll see you in the next one.